How's everybody doing out there? So in section 3.2, what we're going to cover is the addition rules of probability, which are going to be related to OR type problems, and complements, which are going to be related to finding the not of a problem. So the OR is broken up into two separate categories, whether the data overlaps or whether the data does not overlap. So when the sets of data does not overlap, this is what's called mutually exclusive or disjoint. And so if you remember anything about set theory, so this would be a little diagram of what this would look like. So we have two circles where there's nothing overlapping in the middle. And when they're disjoint, this is kind of the best case scenario. So things that could be disjoint would be flipping a coin and rolling a die at the same time. Since neither one of them relate to the other one, there's definitely going to be no overlap. So even certain cards can have no overlap as long as you choose the conditions correctly and stuff. So, all right, so let's take a look at an example here real quick so we can see what we do here. So suppose we roll a fair six-sided die once. What's the probability of rolling a 4 or an odd number? So again, just to remind us, hold on. What we might want to do is list out what the sample space looks like for a fair six-sided die. So in this case, we've got 1, 2, 3, 4, 5, and 6. And so what we're trying to do is we're trying to find the probability of 4 or an odd number. So again, this OR is related to our addition rule that we're going to be using, even though we haven't formally talked about it at the moment. And so if we were just to think of these each individually, so the probability of rolling a 4, since there's just a single one, is going to be a 1 over 6. And the probability of rolling an odd number is going to be either 1, 3, or 5. So we have 3 of those. And if we add them together, it looks like there's a 4 over 6 chance of getting either a 4 or an odd number, which you could reduce down, of course, to 2/3. So when there's no overlap, what we can do is just add them up completely, and we don't have to worry about anything that goes along with it. So in the green, we've got our formal rule for the addition rule for mutually exclusive events. So if A and B are disjoint, then the probability of A or B occurring is the same thing as just the probability of A plus the probability of B. And then I added this for the set theory people from Math 110. This is what this would look like from a set theory perspective. So N means the number of elements in A union B would be the same as the number of elements in A plus the number of elements in B. And so this isn't restricted to just two sets. We can do this with any number of sets that we have. So our final rule down here at the bottom shows that we have the probability of an A1, A2, A3, or A up to K. Then we can just add each one of these individually as long as they're all disjoint, and that's going to give us our probability for these. All right, so let's take an example with our decks of cards and see how we do with these. So suppose we draw one card from our standard 52 card deck. What's the probability that we get an ace or a face card? So we're trying to find the probability of an ace or a face card. And if you remember from the last section when I described the sets of cards for everybody's, aces and face cards are different. They're totally separate beasts. There's no overlap or anything like that. So what we can do is just take the probability of each one of these individually, add them up, and that'll be the probability of our OR statement. So since there's 4 aces in the deck, the probability of drawing a 4 or an ace is going to be 4 out of 52. Since there's 12 face cards in a deck, the probability of drawing a face card is going to be 12 out of 52. And then finally, adding these up, since they have common denominators, we can just add across the top, leave the denominator alone, and we get 16 out of 52. Now, I know this can simplify, but I'm just going to leave it like this for now. And I'm not going to turn these into percentages either. I'm just going to leave these as fractions. All right. So for B, what's the probability of getting a number card or a red jack? So the probability of a number or a red jack. And so again, jacks is part of the face card group, so it's definitely not a number card, so we don't have to worry about any kind of overlap or anything. So we're looking at the probability of a number plus the probability of a red jack. And so if you remember, there's 9 number cards per suit, and since there's 4 suits, 9 times 4 gives us 36. So there's 36 total number cards. And then as far as red jacks go, there's the jack of hearts and the jack of diamonds. So there's only 2 red jacks. So we're going to get a probability of 2 out of 52. And then again, adding these up, we get 38 out of 52. All right, so for the last one, what's the probability of selecting a red card or a black card? So in this case, probability of red or black. And so if you remember, there's 13 hearts, 13 diamonds. So those make up all of our red cards. So if we add those together, that's going to give us 26 out of 52. And the black cards, there's 13 spades, 13 clubs. So again, we're going to get another 26 out of 52. And so when we add these together, we're going to get 52 out of 52, which is pretty much, which is 100%. So in this case, there's going to be a 100% chance that we're going to get one or the other, which makes sense because in our 52 card deck, that's all that exists for those. All right, so I'm going to have you guys work on practice 1, practice 2, and then we'll come back at the next video and talk about what happens if the sets are not disjoint. So good luck.